Okay, so just to go back to what we were talking about last lesson. And for the video, this is Richard waiting for the class to come to attention. And we're there. Okay, so from last lesson, the last couple of lessons is all about defining what the log function is and learning how to use it. Now, I know from previous years of work, sorry if that scares me, from previous years' work, you've already come across log before. Hopefully we're getting more clarity around the log function. Secondly, I know that from previous work you've looked at log rules, and I asked you to revise those prior to starting this unit, and we will in fact come back to those log rules after we've looked at how to graph it. So that is all coming along, but we've looked at some basic properties of log rules. Just a reminder that that's the relationship between the three parts of an exponential function, and with the idea that if we want to get to the exponent as opposed to the base, the inverse function is log, based upon that definition there. And arising from that, we've got a bunch of log properties, I guess log laws, but they're really log properties, where log base a equals 1, log base a1 equals 0, because a to the power of 0 equals 1. Log base a0 is undefined, it does not exist. Log base a to the power of a is equal to a, which is a bit random, or more specifically, log base a to the power of n is equal to n for reasons that we've gone into. And we're going to, that rule is actually used a fair bit, that one there, but we'll get to it later on. So in this one here, we were just asked to find the inverse function. We can see that if we start off with a base to a power, then by applying the usual standard method for working out an inverse function by flipping the x and the y, because an inverse function is the flip of the coordinates. Ambrosia, you okay?
They're finding my highlighting this case. Oh my God.
Okay, that's all right. Importantly, Jeremy, if it works for you, then it's a success. Then the inverse function is given by log x, if it's 10 to the power of x. So in general, we would say that the inverse function will be log base ax for a function which is a to the power of x. And the usual limitations of that apply. So for example, a can't be a negative number, etc., etc. Then we had a look, excuse me, we had a look at the graph, and I'll just quickly flick over to the graph so you can see it, just to remind you, and then we'll have a look at a transformation. So here is the graph of log x, the screen. So I'll just zoom up a little bit. So we explored the idea that just like an exponential graph has a horizontal asymptote, for a log graph, we have a vertical asymptote along the y-axis. And in an exponential graph, we have a y-intercept of 1 and no x-intercepts. In a log graph, we have no y-intercepts, but we do have an x-intercept at 1. Okay, because log base a 0 is equal to 1 for all possible bases, all legitimate bases. Remember, you can't have a negative base, etc., etc. Okay, and it will always be that. Okay, so it'll always come through at 1 regardless of the base. So this is log x, which means it's base 10. What's the other common base? Log base. Sorry? No, actually not. No, you don't try and guess it. Either you know it or it's one of those factual things. Either know it or you don't. The most common base other than log base 10 is log base e, and e is a value 1.7 something. And I can't remember exactly. It's in your textbook, but it's something along the lines of, it occurs in nature a lot, and it's got to do with a magic number that a base approaches when you have, I don't know, a population doubling every 2 years or something like that. I'd have to look it up properly. That was really weak what I just said, but it's got something to do with that. It occurs in nature a lot, but it also occurs in finance and all over the place. But that's why it's called the natural logarithm. So it's the inverse function to the base. So if I go y equals ln e, ln x. Ln is the shortcut for log base e, natural log, ln. You can see that the natural log, this is a different base. The natural log has a sharper gradient, but nevertheless it cuts through at the same point, 1, right? Because regardless of what the base is, it'll cut through at 1 because log base a 0 is always 1. Yeah? Okay, as usual, these are effectively parent functions. So this one I just typed in there, the black line, is the parent function for the natural log. This purple line here is the parent function for the log base 10. I can do another one, which is log base 2 of x, like so. That's the parent function for the log base 2. So our parent function is always log base something x. And our transformations, therefore, are a result of applying our usual set of transformations to a parent function. Right, so Ambrosia asked, why does it, or why do they all go through 1? So I'm going to go back to Air Sketch. And if I was sketching this for real, good morning, Ansel. If I was sketching this for real, rather than just looking at Desmos, let's have a quick look at what we would do. First of all, so I'm just going to go for Y. So I'll just call this sketching log base AX. Okay, so we go through our similar principles. First of all, we need to have a basic idea of the shape of the graph, which is kind of like that, right? With a vertical asymptote. We know that's the shape of it. Well, we need to know the y-intercept, the x-intercept, and well, there's going to be no turning points. So really just a y-intercept and an x-intercept. So I've kept it deliberately general at log base AX to show you what I mean. Because Ambrosia, if I can sort of show you what it means for log base AX, it means it works for 2, works for 10, works for E, works for any number. All right. So y-intercept. That's what I'm about to prove. Yeah, that's what I'm about to prove. So first of all, y-intercept, none, as vertical intercept at x equals 0. Okay, so sorry, did I say vertical intercept then? Vertical asymptote at x equals 0. So there's no y-intercept. X-intercept. Now, every single function that we have looked at, we have found out x-intercepts exactly the same way. And what is that? Beg your pardon? Y what? Y equals 0. Yeah, okay. So every single time we want to find an x-intercept, remembering that on a pair of axes, the x-intercept is anywhere along this line, but anywhere along this line has a y value of 0. Okay, so we let y equal 0 and we solve. So that means we would have 0 equals log base a of x. Huh? Oh, gosh. Sorry. So it is a bracket. I apologize, and you'll find that I will invariably switch between notations of not having brackets and having brackets. I try to use brackets as much as I can because I want to reinforce the idea that log is a function and that the x is the input to the function. Okay, so I will try and use x particularly when I'm looking at it from a sketching perspective, but I really should use it consistently. But it is such a common function that you will often find that the brackets aren't there at all. It's sort of treated a bit specially. It probably predates function notation, is probably why it doesn't have the brackets in it in a lot of instances. Okay, so we need to solve for x. So we're going to use our understanding of logarithms in order to reorder this into exponent form. Okay, so we have got a to the power of b equals c. A to the power of b equals c. So if I write this in exponent form, I get x equals a to the power of 0, which equals 1. Okay, now that short little bit of work there was independent of the value of a. The only thing I'll say is that a has to be a positive number. If a is negative, things get a bit weird. Okay, which is the same as an exponent graph as well. An exponent graph has a positive base as well. We never look at a negative base because it ends up not being a function. It's a relation, but not a function. No, not really. I haven't set up a QED means thus it is demonstrated, and I didn't set up a proposal to start with.
So, but we can say that this shows that it will always intercept the parent function will always intercept the.
Yep. Parent function. Yep. Perfect. Base function or parent function. So does that make sense, Ambrosia? Because I didn't say what a was, you can see that it would work for a equals 2, a equals 5, a equals 20, a equals e, a equals 10. And so I have, switcheroony time, this magical rainbow effect happening here, where you can see the gradient means it approaches 1 at different rates, and after it leaves 1 at different rates. But nevertheless, there's a terminus there, right, at 1, a bus terminal. Alrighty, so it does affect it. Let's have a look at it. Since you mentioned it, this up the top here is log 2x, right? So log 2x is a horizontal dilation, right? Just give you a moment to think about what effect putting a value on. So remember, we're adjusting the input. We've doubled the input. So if I input 1, it takes the log of 2. If I input 10, it takes the log of 10. So I am consistently doubling the input. That's the transformation. So I'm not doubling the output, which would be 2 log x. I'm doubling the input. What effect would that have on the graph? Give you a moment to have a look at that. Stretch or compress? All right, let's have a look at it. Has it stretched or compressed? Hello, Archie. It's compressed. You're right. It is compressed towards the vertical axis. That's the trick. Yeah, it's stretched or compressed towards the vertical axis. And it kind of makes sense if you think about it. Look at where it's gone through. Beg your pardon? The original is blue. You can see the colors here on the side. Blue and red. So you can see it's compressed. You can see that I've just got the arrow underneath it. The x-intercept is now 0.5 or a half instead of 1, which makes sense because now, in order to get the log of x equaling 0, we need the input to be 1, which means the x value has to be a half because a half times 2 equals 1, right? That's how it works. So that means that everything has been pushed back this way, and hence it's compressed towards the y-axis. Ooh, okay. Beg your pardon? Yes. Did you ask what would it look like if it was stretched away? Yes. So it's kind of, you know how like So everything to do with the x is, until you're used to it, is kind of counterintuitive. So log of x minus 2 will actually make it go to the right. 2x compresses it. Half x stretches it. Or it kind of everything is opposite to what you expect. So the thing I love about Desmos, even more so than your calculators, is that it's so easy to just explore with stuff. So there you go. Down the bottom there, it's in a different blue color, so it's really hard to see very well. But this is log of a half of x. Just for the video's sake, I'll just use the mouse here. So you can see that in order to get log of 1, x would have to be 2, right? Because half of 2 is 1. And log of 1 is where I get y equals 0. So you can see that with this blue line here, there it is there. It's cutting through at 2. Now, something else that I thought might be interesting for you to see is this one here. So this is log 2x, this red line here. I'm about to put a green line on, and the green line is actually a, what do you call it? It's a, what is it? What is that second one down on the screen? What kind of transformation is it? It's a, it's not a dilation. It's not a dilation because I've just got log x. Yeah, it's an upwards or down. It's a vertical shift, or a translation, if you want the fancy schmancy word for it. Now, the reason why it looks scary is it's because it says log 2. But if I put log 2 in my calculator, how many answers will I get back? 1, right? Log 2 has a specific value, so it is a constant. If it's a constant, it's just a number. If it's just a number, then all I'm doing is I'm taking your parent graph of log x and I'm adding a value to it. So it's just going to go up by whatever value log 2 is. I don't know what it is. You can use your calculator. We can use our calculator and find out. So all I'm doing is I'm adding the value 0.301 to it. That's just what log 2 is. Okay, ready for it? This is cool. Parent graph is the purple one. Log 2x is the red one. This next one is going to be green. It's log x. It's a vertical translation of log 2. Ready? Oh, it's blue, sorry, light blue. Okay, Zoe's blinking a bit. You ready? I'll turn it off. It's exactly the same graph. Okay, so what's happened is that a shift of log 2 shifts this blue graph directly up log 2 units everywhere. So again, I'm using my fingers instead of this. Everywhere there's a shift of 2 going upways here, and it has the same effect of doubling the input. Now, we're not up to this yet. I'm just writing on the whiteboard, just saying that for the video, but it kind of shows, does it not, that log 2x is the same as log 2 plus log x. And do you remember the log law? That log of AB is equal to log A plus log B. There you go. Graphically, you can see it working from a specific example, but graphically you can see it working. Post the graphing part of this unit, we will revisit these laws and make sure they make sense to you as to why they work. But graphically, can you see that's an example of it working right there? That log 2x is the same as log 2 plus log x, or vice versa. Anyway, that's just a by the by. The important thing is I've just shown you that for a weird value, that vertical translations work as well. So just a reminder that when you're doing transformations, you need to have an understanding of the transformations so that you can apply them to the graph. And for all practical purposes, the reason why we want to have a good idea of what transformations do is simply so you know what you're about to draw. And so you have a good expectation. But ultimately, your graph is governed by being able to work out the x-intercept and the y-intercept. So I'm just going to make up an example now, and I'm going to see how we go with this example. Because I'm making it up, the chances that I'm going to get something which is actually quite reasonable is actually quite small. But just bear with me, right? So I'm just making stuff up. So I'm going to sketch a transformation. I'll just keep that zoomed out. Okay, so the example is going to be y equals 2 log x minus 10, something like that. I've got no idea how this is going to work out. Okay, but we can have a rough idea, right? If I draw my graph, this is kind of what I do in my head, really. So a rough idea. I know that because it says x minus 10, I'm going to have my log graph shifted to the right by 10 units. And I know that because of the log function being doubled, I'm going to have a compression or a stretch. Stretch, because this is affecting the output, not the input. It's going to be a stretch. So it's going to be a stretch away from the x-axis, like so. So a stretch and a translation. And so I would expect it's going to be something along the lines of like that. That's going to be 11. And that's going to be at 10. Something like that. I'll confirm it all, but it's going to be something like that. Okay, so yeah. So remember, any sort of effect on the input that affects the x value directly is going to be opposite to what you think until you're used to it. What's that? Yeah, which works in polynomials and doesn't quite work for anything else. But yeah, and don't forget though, if you remember the opposite thing, it also applies for dilations as well. Yeah. Okay, so we know that there's not going to be a y-intercept. Okay, but there's going to be a vertical asymptote at x minus 10 equals 0. So you see what I did? The input to the log function is going to be x minus 10. So that's where the vertical asymptote is going to be. So the vertical asymptote is the value that the graph reaches towards but never hits. Because log of 0 is not defined, that ends up being the where the vertical asymptote is going to be. So I need to sort of solve. This is like the null factor law, right? Sophie, it's not quite. I need to solve what the log of 0 would look like, and the log of 0 is x minus 10 equals 0. So I'm setting the input equal to 0 and then solving for x. So that gets me that. There's no horizontal asymptote. I didn't mean to write that. X-intercept, set y equal to 0. So I have 2 log x minus 10 is equal to 0, which is the same as log of x minus 10 is equal to 0. So I can divide both sides by 2 and it doesn't affect it, right? Now again, base 10 to the power of 0 is equal to x minus 10. Like so. X minus 10 is equal to 1, and I'll just keep it on the same slide. X is equal to 11. So that working out sort of confirms what in my head I'd be thinking I'd be seeing. Yeah? So that's confirmation of it. And that's the graph done. What I thought of, because I actually wrote it down, I'm not going to write it again. I'll do another example. I'm going to try and get a vertical, a y-intercept this time. So, oh well, just make it log equals x minus 1 or something like that will do it. So this is example 2. Let's go for, I'll just use the other notation as well. F of x is equal to log of x plus 1 minus 1. I think that should be all right. So importantly, in my head, again, so I'm just thinking about it. Give you a second to think about it yourself before I uncover it. Think about what the graph would look roughly, that's all. I genuinely don't know what the x and y intercept is for this. Okay, that's enough thinking time. In my head, I'm thinking, okay, I've got a translation to the left of 1, so it's going to have a vertical asymptote here, and then the graph is going to, let me see now, it's going to go up by 1, down by 1 as well. So I don't know, it's going to, I think it might be like that, something like that. I don't know, and I certainly don't know, but out of this, importantly, I can see that I'm going to get a y-intercept and I'm going to get an x-intercept. I just need to confirm where that y and x-intercept is. It might be above, it might be to the left. I don't know. That's why I need to do my working out. But importantly, because I know what the shape of the log graph is, and because I know what the effect of a transformation is, I know it's worth looking at it. I know it's worth solving it. So here we go. So y-intercept, let x equal 0. So that means I've got y equals, notice I've moved to a y now instead of f of x because I'm working at a y value, equals log of 0 plus 1 minus 1. So it equals log 1 minus 1, which equals, and you know what? That's my exact answer. I'm just going to go for, well, what's the log of 1? It's 0, isn't it? Okay, so I can substitute 0 for that. And so I've got a y-intercept of -1. Wow, I think my graph might be all right. Yeah, it's just happenstance. X-intercept, that's where I let y equal 0. So I've got 0 is equal to log of x plus 1 minus 1, like so. Add 1 to both sides. Use my log understanding. So 10 to the power of 1 equals x plus 1. And therefore x equals 9. That was nice and tidy. I didn't mean it to be so tidy, but I'm pleased with it. So you've got your x-intercept, you've got your y-intercept, you've got your vertical asymptote. And so we can, I didn't actually formally work that out, so I'll just do it here. Notice it's not a coordinate, by the way, it's an equation. X equals -1 is the equation which gives me the vertical asymptote. And then I can go for it and draw, imagine I'm using a pencil. Totally completely out of whack. Was it 10? That was 9, wasn't it? Done. What do you reckon? That's all right, isn't it? But again, it's just a whole heap of practice, right? You've been doing this for weeks along weeks, just different functions, but it's the same process. What does the parent function look like? Once you've got that sorted out, the next question is, where's my x-intercept, y-intercept, and other special things like for a quadratic special, like for a quadratic, it might be a turning point. For a hyperbolic function, it might be the vertical and horizontal asymptote. For an exponential graph, it's a horizontal asymptote, and for a logarithmic graph, it's a vertical asymptote. Special properties of that graph, which you know about because you know the shape of the parent, and then applying those transformations as you go along, x-intercept, y-intercept, etc. Okay, so that's basically all the stuff that you tend to do. What I'd like you to get used to in this, I'm going to set you to work now for the next half an hour, and all you're going to do is you're going to practice transformations. Now, in the textbook, there's not as much sketching as I would like to be involved there, so I'll point you in the right direction in a second, but I want you to be doing some sketching as well. So in order to confirm your answers, though, I want you to do one of two things. Number one, if you've got your graphics display calculator, I want you to use it, because if you don't practice using your graphics display calculator, you'll continue to have the pained expression on your face that Ansel just showed us. Okay, so you bring your graphics display calculator to every lesson and you use it as often as you can. Otherwise, you will be absolutely at a disadvantage in 2020. Absolutely. Secondly, if you don't have your GDC today, I forgive you. Use Desmos to do it. Desmos is much easier and faster. Desmos is Life, LYF 3. But it's not what you get to use in the, what's the name? Yeah. Bye. I haven't finished giving instructions, but see you later. If you want to, but I'm about to tell you what you need to do. So what we're going to be doing is exercise 4J. As I said, there's not a lot of sketches there, but I think it would certainly be worth, in question 1, for example, drawing a sketch of A, B, and C, and then confirming them on your GDC. Question 3, 2 and 3 get you to do a sketch. Again, the answer's in the back of the book, but use your GDC to confirm, and then move through question 4 and 5.